Okay, so we're going to start something new. We're going to start going into circular motion. And one of the things we're going to do is gravity. We want to figure, it turns out, why are there 12 months in the year? That's not an accident. So we won't probably answer that question today. We'll probably answer this question tomorrow and throughout the week. We're going to find out, why are there 365 days in a year? It's not an accident. Why are there 12 months in a year? It's not an accident. You can actually understand this. And it's going to deal with circular motion. But before we get to that, I want to talk a little bit about gravity. And then one of the big examples we'll do with gravity will be planetary motion. Okay. So I want to talk about Newton's law of universal gravitation. Okay. So what is this? This says, let's say you have you're going to have a point. Okay, let's go this way here. What do you think it means to be a point? What is a point mass? It's going to be well named. Yeah, you can have some object here. Imagine all the mass of that object is concentrated at one single point. So point mass is, instead of having some big blobby thing like that, you take all that mass and you concentrate it up. So I have one point mass. I'll call this M sub 1. And I'll have another point mass here, M2. So these are 2 point masses. And let's say there's a separation distance here, R. So R is your separation distance. Okay, what happens here? Well, it turns out that one property of mass is that it exerts a gravitational attraction on the other. So mass exerts a gravitational attraction on another mass, on other masses. After I mention this, what I'll do is later on I'll explain. Einstein comes along and says, this isn't quite right. And Einstein's going to come along and look at this from another point of view. We're not going to do it from that point of view because it turns out the mathematics is fallacious. Even if you're a math and physics major, the mathematics is fallacious. But the concept is relatively simple. So we have point masses here. There's going to be now, this is a property of mass. That mass exerts a gravitational force on it. Okay, so property of mass. So this is how we're going to do it. I'm going to say the gravitational force that this object exerts on this object is this one. So this right here, the notation I'm going to have here, I'll even write here. So this is going to be the gravitational force at mass 2 exerts on mass 1. Well, what is mass 1 going to do to mass 2? Pull it in. By gravity. Sure. What's another? Okay, so this right here, this is going to be the gravitational force that mass 1 exerts on mass 2. What do you know about these two forces here? They have to be the same, but opposite direction. What law? Which law is that? That there's equal and opposite forces? Newton's. That's the third law. So again, this object here puts a gravitational force on this one. We're saying because matter now has a new property, gravitational attraction. That's here. And then this one also exerts a gravitational force on this one. And these are equal and opposite by Newton's third law. So the force here, force of gravity, that 1 exerts on 2 is minus the force of gravity 2 exerts on 1. And this is by Newton's third law. Okay. The question is, what is that force given? So we would like an expression for this. Okay, what does that have to be given by? And this is where Newton actually figured this out and figured out why it had to be this way. Okay. So, what is this? I'll put this over here. Well, look at the magnitude of this force of gravity. So I can either put 1 acting on 2 or 2 acting on 1. It doesn't matter what I put down. Okay. I'm just looking at the magnitude of this gravitational force. Does anyone know what that's given by? Or let's say, what is it proportional to?
Mass time acceleration.
We'll hold off on that part. We'll get to that part in a second. Does anyone know? It's not one, but obviously. Okay, Newton said that gravitational mass, if the two masses are good on each other, it has to be the product of the two masses. Okay. So in other words, if you had bigger point masses here, you'd expect a larger gravitational force. How do you think it's going to vary with the distance? Yeah, it's gonna. You'd imagine if you had two objects further away, the force would be smaller. If you're closer together, it would be larger. It turns out it goes as r squared. There's a reason why he postulated this. Okay. So, what's this directly proportional mean again?
This one increases the other will increase.
Yeah, whatever you do to this side, you do the same thing on this side. How do we say if you have two things directly proportional, how do you make them an equality? Yeah, I have to put in a multiple to the constant. Okay, so to make an equality here, you introduce a multiplicative constant. I actually look at the magnitude of this force. That's given by capital G. That's our multiplicative constant, M1, M2 over R squared. And this grand expression here is called Newton's law, actually Newton's universal law. Gravitation. Okay. That changed the history. That changed history. Okay. Does anyone know why Newton just wasn't sitting around one day? No, I think gravitational force was the product of the masses and over the distance. There's a reason why he postulated. Okay. Does anyone know the history? It's actually really cool. Here's the history. Yes.
Is this the like one where the apple was good at?
Which evidently did happen at some point. But no, he didn't come up. He realized that led him around the right direction. But it is connected with that. But he's trying to explain some of these data. Does anyone know whose data he's trying to explain? It's really, really cool. Okay. A little bit of history is important history. So normally I don't do history stuff, but this is really important history. Okay. They had the ancients had really excellent data on these, but they got better. Anyway. Okay, so the first one that came along was Tycho Brahe. Okay, what he did, he took really accurate data of basically the planets going around the sun, in particular Mars. So he took very accurate planetary data. Tycho Brahe is one of those, whenever you hear Tycho Brahe, you always hear this story about him. There's kind of two stories. One of the stories you hear about Tycho Brahe starts off with his nose. Is there a reason why? He didn't have a nose. He lost it in a duel. So he lost his nose in a duel, so he had like a little piece of leather over his nose. And I guess he could replace it with something for when he went to fancy. So he didn't have a nose. The other one you hear about is that he basically, I guess, when he lived, it was not considered polite to basically ask you to leave yourself at somebody else's house. And he was at a party, I guess, drinking off the and was too embarrassed to ask to use the bathroom. And so we went on a carriage ride home, and basically the bladder burst and he died of his pain. Those are the two stories always heard. Okay. So what, a moral lesson here: if you're at somebody's house and you have to pee, you ask them to pee. I don't want to die like that. Saved your life. PSA. Good we know. Okay. This data goes to somebody. Who does it go to? Kepler. Okay, so Kepler analyzes the data. And he generates what are called Kepler's three laws. Okay, we're going to look at the three laws later on, but right now we only need the first one. Okay, does anyone know what the first law is? So Kepler's first law. Okay, what's Kepler's first law? I'll give you a hint. You know it when you're in elementary school. In elementary school, you draw pictures of the solar system, and how do you always draw? The sun. And you draw these orbits, and the teacher tells you that's an ellipse. And when you're a little kid, you think that's a cool word. But you draw a little ellipse. So the first law states that the planets orbit the sun in an elliptical orbit. Where the sun is at one. I'm using these words here, you haven't used them. Okay, so let's do a little review of some analytic geometry. What is an ellipse? They look exactly like an oval. Okay, they do look like an oval. But what actually is it? It's really kind of cool. You may have actually made these in high school. Okay, so if a kid wants to draw a really nice oval, what should they do? They take a piece of cardboard, they put down two thumbtacks, and then what should they do? They tie a string between this thumbtack and this thumbtack. They put their pencil here and they pull it top like this. And then they go around like this and they make it perfect. Okay? That's an ellipse. And so this is what an ellipse is. So if I have a point here and a point here, this is called a focus. This is a focus. This is a Latin word, so when you have a US ending in a word, it's Latin, so the plural is actually foci. So the combination are called foci. Okay. I put a string between the two. So here's like a string here like this. I call the distance from here to this point here R1. From here to here, I'll call this R2. So imagine I have a thumbtack here, a piece of string, and I have my string like that. I can then move out like this. I can make a perfect ellipse. Well, what does it mean? That means if I'm over here, what do I know about this term plus this term? If I measure this length plus this length, how does it compare to this length plus this length? It's the same. If I'm over here, how does this length plus this length compare? It's the same. That's what an ellipse is. So an ellipse is, we've spent a lot of stuff on it. An ellipse is the collection of points. That just means the outside part here because there's a whole bunch of points there. Whose sum of distances between two fixed points is a constant. What that means here, if you look here, here's a fixed point, here's a fixed point. I call this R1 plus R2. An ellipse has R1 plus R2 equals a constant. So if I take this distance plus this distance, no matter where I am on that ellipse, I get the same value. If I draw this thing out like this, that's the saddest looking ellipse I've ever seen. That's not much good. Oh, anyway. Doesn't matter where I am on this side of the ellipse here, the distance from here to there will always be the same value. That's an ellipse. So Kepler's data showed that. So Kepler's data clearly showed that basically the planets were going around the sun in elliptical orbit. The question is why? Okay. So the question is, why does this happen? Why do planets move around the sun in a circular orbit? I mean, in an elliptical orbit. So, okay, just kind of complete the picture there. So what this is stating, this law, that if here's the sun, if here's the Earth, this right here is the full sun. This is the focus. So the sun is at the focus and the planet is here on the.
What's the other?
That could be another object. But in our solar system, so the sun could be either be here or. So that's what you have. That comes from the data. What Newton showed, and I'm not going to show the calculation, it uses actually a fair amount of sophisticated math to do it. What Newton was able to show is that if, so Newton showed that if gravitational force between the Earth and Sun or let's just say between the planet, it could be any planet, and Sun is basically proportional to M1, M2 over R squared. Like this, the motion has to be an ellipse. Orbit. Must be. That's why he calls it. That's really cool. Initially, he actually did the calculation, and he thought he was wrong because basically he put in some wrong values. And then there was a very famous astronomer by the name of Herschel. Herschel and Thomas Young and also Huck were trying to figure out what has to be the gravitational force to make an ellipse. And Herschel realized, well, the only one who'd be smart enough to figure this out would be Newton. He goes to Newton and says, oh, so what has to be the gravitational force to make the planets go around in an ellipse? He says, oh, it has to be basically 1 over r squared. And Herschel went, how do you know that? Oh, I worked it out. Here's the result. And over here someplace. But he said it didn't work because the data was wrong. Didn't describe things correctly. Herschel looked at it and immediately realized that he had the wrong value for the size. And as soon as he corrected that, he realized that was perfect. And so that was absolutely instrumental because that was absolutely key in the development of the English language. So, I mean, if you look at it, this scientific idea here, that entirely feeds into the English Enlightenment. Remember what happened with the English Enlightenment? What happened there is that you had the Reformation happen. That split basically Europe between Catholic and Protestants. It led to the 30 Years' War, which was a complete disaster. Left Europe completely divided. And then along basically came the whole idea of enlightenment, which was basically, how do you know something? Do you know something basically because somebody told you something, or do you know something from observation? And actually, this is one of the few, this actually here led into a lot of the ideas behind John Locke, the epistemology, how you actually understand something. And this was absolutely instrumental, which then led actually, if you look at our case here, the Declaration of Independence, we hold these truths to be self-evident that all men are created equal. Okay, why is that statement coming in here? That's actually Enlightenment philosophy. So a lot of those ideas in the Enlightenment actually are absolutely instrumental for this development. Really, absolutely. That's a really quick version. You can actually develop this in a lot more detail. Absolutely amazing. That's the only time we really stop and talk about this. Okay, what else can you do? Now, to do this problem, Newton had to do something else. If you want actually more of this kind of the history part, I think I got this right. There's a professor of history, philosophy. It's actually, he calls it intellectual history. His name is Alan Forrest, and he has an absolutely brilliant series of lectures on this. You can get them from the teaching company. Absolutely incredible. And he goes into all the detail behind this. I mean, he develops it a lot better than I can decide about that. Absolutely amazing. Okay, now there's one other thing. The equation, let's actually talk about this. Let's ask, what is G? So G is called the universal gravitational constant. Do you think this is large or small? Well, you ultimately have to measure it. Turns out it's really small. You know this every day. Why can't that be large? If that were large, what would objects be doing? Yeah, they'd be falling. I mean, that camera would start coming from me. I'd start going toward it. I'd be going through the wall. Things would be falling us out. That doesn't do. So you know that the only way you can really get this to be large is if you have one of these masses be gigantic, like the Earth and the Sun. So this G is really, really small. In fact, the way you measure it, if you look up there, you can see something over here. You can't really see it here. This device here, you have a ball here and a ball here. You actually get that rotating like this. And actually, by doing that and some other measurements, what you can actually do is it's a way of, and the experiment has to go on for days or so. You can actually measure what this is. So that's what that device up there is measuring. Okay. It's called a Cavendish balance. So this G is very small. Turns out to be 6.67 times 10 to the minus 11. Now, we need some units here. Let's figure out the units. What do you have to measure force in? Newtons. So we're going to put a Newton here. Now, a mass times mass has units of what? Kilograms squared. Okay. So, what else have to be the units here to kill the kilogram? This would be the Newton, right? This would give us a Newton. This gives us kilograms squared. I have to kill the kilograms squared. So this has to have other units. Other units of what?
Over, over kilograms squared.
Yeah. So the kilograms, so this is gonna have really weird units. So the kilogram squared of this unit is gonna cancel the kilogram squared from the masses. What else do you have to get rid of? Which would be units of what? Meters squared. So I have a meter squared here. I have to get rid of the meter squared of the denominator, so what else do I need? I need meter squared in the numerator. So the meter squared here, cancel the meter squared here. The kilogram squared here, cancel the kilogram squared there, and I'm left with it. Okay? We're going to get something similar in second semester when we do electric charge. Okay? Now, there's another problem Newton had. When is this equation true? Only for point masses. So let's ask how can you apply this here? Which is only true for point masses. To objects like the sun and planets, which are not point masses. Okay. So, what do you do? This is actually going to lead to the development. This is where calculus. Well, let's say I have something like this. Here's the sun. And here's a point mass. This is not a point mass. So here you are, your Newton. You have your brand new gravitational force equation. Everything's all like great, but you can't apply to this because basically this is the sun, which is not a point mass. Okay, what could you do? You only have one equation for a point mass. How could I view this object as being made up of? Yeah, you can say, oh, well, I don't know what the sun is, but I can treat the sun as a whole bunch of little point masses. So treat the sun as a collection of point masses. So I can, here's my little point mass, so I'll call this a point mass. And I can look at this right here, I can look at this force here, I can call this will be the force from basically the point mass on M2. Then what would I do? Then I look at, oh, this little point mass. Here's another little point mass. I can look at the gravitational attraction between this point mass and this one. So this is the force of this point mass. I can do that for this whole thing and add them all together. Okay. That actually is in the process called integration, and this is actually what led to it. So Newton actually had to go through and do this problem, and he had to invent calculus to actually solve it. But I showed you this is fine. Okay. So Newton invented calculus to solve this problem. The result turns out to be really, really easy. So Newton goes through this whole big thing. What does he find out this is reduced to? It's really amazing. Newton showed that if one of the objects is a spherical, it can be treated as if all of its mass is at the center. Let me actually prove that mathematically. Let me draw that picture. It's going to be a real easy result. So here's the sun. It has some radius, I'll call it RS. Let's say the distance from the center of the sun to the Earth is, so let's say here's. So Newton said if you want to find the force from the sun, and M2, you can take all that mass of the sun and concentrate, pretend all that mass is actually at the center. So if this reduces, and have like a little dotted line. That's the former radius of the sun. I can take all the mass here, I'll call this M sub S. I can treat it as if all the mass here is at the center. Okay, and then here's M2. And this is R. Now what does this look like? This looks like two form masses. This is just two forms. So you could say that the force between the sun and the Earth, and the sun too. Okay, it's just this G mass of the sun, M2 over this R squared. So it doesn't matter the fact that it's not a point mass. You can treat it as if all the mass are at the center. Does that make sense? I didn't prove any of this. The proof for this is actually, that's not needed. But we get a PSA here. If you're doing any of these problems here, if you create new mathematics to basically solve your problem, I'll give you a name. You don't have to take the final, you don't have to take second test, you don't have to take, you invent new math in this course, I'll make sure you get an A first lesson. You don't even have to bother to come to class. I'll just give you an A, we create new mathematics, you get an A both semesters. That's my guarantee. Good to know. Okay, questions with this? Okay, now let's have some. Y is the weight of an object. What do we say the weight of an object is? So the mass of the object times G. Remember, we said the weight equals mg. I told you I'd prove that later on. Today we get the proof. The proof is going to be ridiculous. Oh, where? What does G become from the Earth? This is 9.8 meters per second squared. I want to show you why this is the case and why G is 9.8. It's not an accident that G is 9.8. Okay, and the proof is going to be ridiculously simple. Okay, so here's the Earth. Here's a proof. Here's the Earth. It has some mass M sub B, and it has some radius R sub B. And here we are. This is us. We have a mass. Okay, what did we say weight really is?
Like how hard the Earth is pulling you towards the center.
Yeah, so if I just say draw the free body diagram for our little for us, what are all the forces acting on us in the picture here? Okay, let's do it. Let's say it's going to be the gravitational attraction of the Earth on us. And this is what we mean by weight. We're going to remember weight is always the gravitational attraction of the object you're on that's trying to pull you toward the sun. Okay, there would be one other thing actually on your what would be. Yeah, there better be a normal force, otherwise what are you doing?
Just gonna keep going.
Okay, you're going to be going through the sun. I won't put that in. I'll just keep it. Okay. According to the Earth is spherical, for all, not quite, but close enough. Okay. Actually, what does the Earth look like? Okay, it's pear-shaped. Now, okay, you know, this is a pear. I'm not saying the Earth looks like this, okay? But if you could actually look at the Earth, it kind of has this like. So this is already a weird. This is already an extreme exaggeration. Okay, but it's pear-shaped. Okay, don't tell anyone I told you the Earth looks like this. Okay, I'll just deny it. I'll just say I didn't tell them. I don't know. It looks like a sphere, but when you actually look at some fractions, you actually have. So it's basically a sphere. Okay, what does Newton say? The Earth is not a point mass, but what can I treat it as if? All the masses at the center. So we're saying that this right here is equivalent to taking this is your Earth. I can put all the mass of the Earth here, and then we're here. And the distance here R is the radius of the Earth. Okay, for all practical purposes, what are we compared to the Earth?
Nothing.
So we could call ourselves a what? Compared to the Earth. A point mass. In comparison to the Earth, we're a point mass. Okay. So what do we have here? We have the gravitational force between the Earth and us. That's equal what? You tell me what that has equal. In this picture. What is Newton's law of gravitation? The gravitational force attraction that the Earth exerts on us is G. M1. What is M1 in this case? Earth times our mass over. Yes. RE squared. Hey, let's give this a name. What do you want to call that? That's it. This is the constant. And define that constant to be something. What do you think you're going to define that little constant to be?
Little g.
Little g. Okay. So this is mg. That's why the weight equals mg. Now the question is, why does it equal 9.8? Well, let's put in the mass of the Earth, and then also the radius of the Earth. That's how I got that. Okay. So what is G? For the Earth. Okay, so we're going to have G equals G, mass of the Earth, over RE squared. Okay, so this is 6.67 times 10 to the minus 11. I'll look up the mass of the Earth, which I don't have in my head, although I probably should. Okay, the mass of the Earth is 5.98 times 10 to the 24 kilograms. over. Then you divide that by the radius of the Earth. The radius of the Earth is 6.37 times 10 to the 6 meters. Comes in squared. Okay, I won't go through and work that out. If you crunch that in your calculator, what are you going to get? 9.8 meters per second squared. That's right.
I didn't figure out what the mass of the Earth is.
Okay, that's going to come from the next part. That's going to come because we know that it takes we know how long it takes the moon to go around the Earth. Turns out if you know how long it takes the moon to go around the Earth, you can figure out the mass.
Oh,
Which sounds like a very stupid thing. But okay. It turns out we even know what the mass of the sun is. The reason why, and I'll convince you of this tomorrow, either on Tuesday or on Wednesday, I'll show you this. We know how massive the mass is. We don't have the mass of the sun because we know how long it takes the sun to go around the Earth to go around the sun. And that actually tells you. Well, that'll be connected with Newton's. Okay. So, suppose you're on the moon. How would you calculate G for the moon?
How it's like it goes around Earth.
Let's say I'm on the moon. I want to know if I can weigh more on the moon. What would you do? Instead of having the mass of the Earth here, you'd have mass of the moon instead of the radius of the Earth, radius of the moon, and then you'd have G for the moon. So you have the mass of the moon over the moon radius squared, and you can calculate this. And it turns out that the G is about a sixth less. So do you weigh less on the moon or on the Earth? On the moon, you're going to weigh less on the moon. You have the same mass on the Earth.
Yes.
Okay, meaning it's the same. Your mass doesn't change, but the gravitational attraction is used for the planet you're on, the moon you're on. Yeah. So weight always refers to basically the gravitational attraction of the planet on whatever's on the planet. That's weight. The actual mass of the object, the mass, stays the same. That's how much matter. Mass tells you how much matter you have. Weight tells you the gravitational attraction of the base of the planet and you. Does that make sense? Okay, so what I want to do tomorrow with this is we're going to do the really, really important calculation. We want to set up the whole idea of circular motion. So we're going to set up this idea of circular motion. We're going to make this, use of this, and we can start asking really profound things like, why is a year 365 days? It's not next. Okay, we'll find out why the year is 365 days. Okay? Why are there 12 months in the year? Again, that's not next. There's a reason why there are 12 months. Okay. Then we can look at some calendar systems too. The calendar systems are really kind of cool. There's 3 big calendar systems in the world. What are they? They fell out. There's 3. Okay, it's based on the 3 great world religions. Okay, Jewish, Christian, Islam. Okay, it turns out this will have an entire connection on basically the how you do the calendar. Okay. It turns out the Christian one's going to be simple. The Islamic one's going to be simple. The Jewish one is really kind of cool. Okay, what it is kind of in between. And so we're gonna find out all that. It's really quite cool. Like, you have to do smart things and you don't have calculators. Okay, or computers. You actually have to. Okay, have a good day.